So hello friends, so today we are going to solve questions from the first session, that was from basically we are going to solve this JEE Mains 2026 session 1 and session 2, and that was on 21st. And all the questions will be from the only physics part. And these questions are memory based. So you might find that the questions might be somewhat different. Okay. So please remember, all these questions would be the memory based question. Okay. And therefore, okay, so the first question, it was asked that a charge of 10⁻⁻8 coulomb is held fixed at the origin, and a charge of 2 into 10⁻⁻6 coulomb is moved slowly from 4, 4, 2 to 2, 2, 2. The work done in doing so is. So in this case, we can draw the approximate figure, and charge is said to be at the origin, and this charge is about 10⁻⁸, and the other charge is being moved from, it is given as 4, 4, 2, and it is being moved to 2, 1, 2, or otherwise let me, you can say it is from 2, 1, 2, and it is being moved to 4, 4, 2, something like this. And let us assume that the charge at the origin is fixed, and let us call this Q1. You can see charge at origin, which is at fixed position. Let us call this as Q1, and this Q1 is given to us as 10⁻⁻8 coulomb. And the other one is a moving charge, and this moving charge is, let us suppose we call this as Q2, and this Q2 is given as 2 into 10⁻⁻6 coulombs. And we are given the initial position is 4, 4, 2. So you can say we are having the initial position of this Q2 is 4, 4, 2, and final position that is our 2, 1, 2, and it is given that the charge is being moved slowly Therefore, we can say that the work done by the external agent will be equal to the difference in the energy. You can say that charge is moved slowly, therefore you can write that the work done will be equal to the difference in the energy. And first of all, let's find out what will be the distance from the origin. You can say distance from the origin and first of all we are going to find our initial distance, and let us call this as our R1, and this R1 will be equal to our 4 square plus 4 square plus 2 square and its square root, okay. And this will be coming as our 6. Then we are going to find out the final distance, and this final distance is suppose our R2, and it comes as our 2 square 1 square plus 2 square and square root, and this will be equal to our 3. Then we can easily find out the change in the potential energy, and for that we know the standard formula, that the electrostatic potential energy of 2-point charge. So you can see potential energy of 2-point charge, which is our U, and that is given as K Q1 Q2 divided by R. And now we can easily modify this according to, we have two positions R1 and R2, so you can say this will be equal to K Q1 Q2 and our 1 upon R2 minus 1 upon R1. We simply substitute the values, we get delta U is equal to, value of K is 9 into 10 to the power 9, and then we have a charge, one charge is our, 1 second, okay. So one charge was our got stuck. Okay, and so we are given that we are having Q1 is our 10 to the power minus 8, and Q2 is 2 into 10 to the power minus 6, and 1 upon 3 minus 1 upon 6. So we get this as delta U is equal to 3 into 10 to the power minus 5 joules. And so that was our first question. Yeah, work done. So this is nothing but our work done. states that find the dimensions of A upon B if this equation is given to us is equal to constant, where P is the pressure, density, and V denotes our speed. And first of all, let's write the dimensions of the known quantities. That our P is our pressure, then its dimension is our M, L minus 1, T minus 2, and our density is our M, L minus 3, and V denotes our speed, that comes as our L, T minus 1, and this T is our time. So you can say this T will be giving us a dimension of our capital T. So let us try to find out what will be, first of all, the dimension of this quantity. So we are interested in finding out dimension of half rho V square. So we are simply going to ignore this half part, and we are going to find out the dimension of rho V square. So this comes as ML minus 3, and we have this as L square T minus 2, and this will be coming as our ML minus 1 T minus 2, and this is nothing but our dimension of our pressure. So it means this is having a dimension of pressure. Now it is quite easy. Therefore we can say that it is added to the dimension of the pressure. Therefore we can say this quantity will be also a representation of our pressure, and we can write this as our M, L minus 1, T minus 2, and we have this as T square. Therefore we get this as A upon B will be equal to, and we get this as our M, L minus 1, and this will be T minus 2 divided by T square. So we can write this as M, L minus 1 and T minus 4. So this is the dimensions of our A upon B. And please, once again, these are the memory based questions. The data and everything might be here and there, but the basic premise of the question is going to remain same. That is not going to change much. So the next question, K1 and K2 are given to us. The maximum error in calculating the value of equivalent spring constant if the above springs are connected in series is. So we have these two springs and they are connected in series, and we know that for series connection, for spring in series, we can write 1 upon K equivalent will be equal to 1 upon K1 plus 1 upon K2, and from here we can write that our K equivalent will be equal to K1, K2 and K1 plus K2, and we simply substitute the values. We get this as our 10 into 20 divided by 10 plus 20, and this gives us approximately 6.67. And now we are going to find out what will be the error propagation. Error propagation. And once again we are going to start from the equation, that is our K equivalent is equal to K1 K2 K1 plus K2, and we are going to take its logarithmic differentiation. we are taking its logarithmic differentiation, and that gives us that their change upon their k equivalent is equal to delta k1 upon k1 plus delta k2 upon k2. And on the right side we can just simplify it little bit. So this gives us delta k equivalent upon k equivalent is equal to, this we can write as k1 plus k2, and this comes as delta k1 plus k2. Okay, and we are supposed to find out the maximum error, so the absolute values are going to add. Therefore, we can say that for absolute error, absolute values are added. Values are added. Therefore, we can write that our delta k equivalent upon k equivalent is equal to delta k1 plus delta k2 plus delta k1 plus delta k2 divided by k1 plus k2. Now we are going to substitute their numerical values, and so first we are going to find out this delta k1 upon k1, that will be equal to our 0.02 divided by 10 and giving us 0.02. Then we come to our delta k2 upon k2, that will be 0.3 upon 20, which will be coming as 0.015, and finally our last part, that is our delta k1 plus delta k2 upon k1 plus k2. This comes as 0.2 plus 0.3, and this comes as 10 plus 20, and this comes as 0.01667. Therefore, we can say total relative error will be equal to delta k equivalent upon k equivalent, and we simply substitute the values, which was our 0.02 plus 0.015 plus 0.01667, and absolute maximum error which is our delta k equivalent will be equal to their summation, and its summation was our 0.05167 multiplied by k equivalent, which is about 20 divided by 3, and this comes approximately as 0.344 Newton per meter. So the second question, and okay, so we have here, okay, so in this case we are given that we have a rod and it is hung by two strings. So suppose this is our, and this is a rod and it is connected with help of string, two strings basically. Okay, and this one of the string, that is our right string, is cut. So we cut this string, and we have to find out the tension in the left one when the string is cut. So we have to remember that as soon as the left string, sorry, not left but right string is cut, okay, the rod will be no longer in equilibrium. Okay, it is going to have tendency to pivot about this point, and so we are going to, and the center of mass, let us suppose that is our somewhere here at C, it is going to start to accelerate in the downward direction. Therefore, under this condition, we are going to find out what will be the forces that will be acting on this rod. So we can say that forces acting on the rod acting on the rod, and this forces when right string is cut. And first of all, there will be weight, mg, and acting downward at the center of mass. So we are going to have mg. So we have weight mg acting downward at center of mass, and second one will be tension T in the left string acting upward. So we are going to have a tension T that will be acting upward. And so let us first of all, you can see, apply for the translation motion of the center of mass. Translation of center of mass, and you can say that is our mg minus t will be equal to mass into acceleration. And furthermore, you can from here you can write that our tension T is equal to our mg minus ma, and let us call this as equation number 1. And now we come to our rotation motion about the left end. Rotation about left end, and we are going to take the moment about the left end, and the tension passes through the point of pivot, so there will be no torque, and the only torque will be because of the weight. So we can say that tension passes through the pivot point so therefore there will be no torque, and you can say that our only torque is due to weight. Therefore we can say that our tau is equal to our mg and our lever arm, that is our L/2. And we know that the moment of inertia about one of the end is our I, and that will be equal to 1/3 ml square. Therefore we can write that our tau can be written as our moment of inertia times angular acceleration, and we substitute the values. We have mg times L/2 is equal to 1/3 ml square, and angular acceleration, where mass this square goes away, and we get that angular acceleration is equal to, and this will be over 3g upon 2l. And we know the relation between the linear and angular acceleration. So we know that our a will be equal to r times alpha. Therefore we can say that our a will be equal to L/2 times 3g upon 2l, and here this l and l cancels out, so we get this as our 3g/4. Now we can easily find out our tension using equation 1. So from equation 1, tension was equal to mg minus ma, and this comes as a 3g upon 4. So we get that the tension T will be equal to our mg upon 4. That was the question. Next question. Next question was from electromagnetic waves, and it states that electromagnetic wave, which is governed by the equation, is incident on the metal surface of work function 2.8 electron volt. The maximum kinetic energy of the ejected electrons is approximately. And so let us write the given equation. E is equal to epsilon naught, and we have this as sine of 3 into 10 to the power 15t plus sine of 12 into 10 to the power 15t, and the work function of the metal, that is our phi, is given to us as 2.8 electron volt, and we have to find out the maximum kinetic energy of the emitted electrons, and that is, you can say, because of the photon energy, and that will be we can say that only the photons with energy which is greater than equal to work function can eject the electrons. So from here you can say that my energy of the photon is given as my h prime times omega. And we know that photons with energy greater than or equal to work function these only can eject the electron. Can eject the electrons. So in this case we are having two different frequencies. This is omega 1 and this is our omega 2. And we are going to find out the photon energy associated with each of the frequencies. So let us say that we have a omega 1 that is equal to 3 into 10 raised power 15, and let us giving us energy E1, and that is our 6.58 into 10 raised power minus 16 multiplied by 3 into 10 raised power 15. So this is approximately equal to 1.97 electron volt. So obviously that is less than the work function. So this cannot emit the electrons. And then we come to our omega 2, and omega 2 is our 12 into 10 to the power 15. So from here we can find out our E2, 6.58 10 to the power minus 16 multiplied by 12 into 10 to the power 15. So this gives us that our E2 is approximately equal to 7.9 electron volt, and which is greater than our work function. Okay, so this is going to eject the electrons. Therefore we can write that our maximum kinetic energy, we are going to use photoelectric equation. Photoelectric equation, which gives us that the maximum kinetic energy is equal to energy associated with the photon and minus the work function. And here energy associated with the photon will be our E2, because that only can eject our electrons. Therefore we can say that the maximum kinetic energy is equal to 7.9 minus 2.8, which gives us 5.1 electron volt. Next question. Okay, I forgot to attach the circuit, but anyways, find the heat produced in the external circuit in 1 second. We have to find out the heat or our 1 second, and that circuit is approximately something like this. And this is suppose 1, 2, 2 and 4, and this is our P. Let us suppose this is our Q, and then we have a voltage source and resistance, and this is our circuit, and this is point A, and this is given as B, and this is given as 2 ohm, and we have voltage source of 20 volt. So let us heat produced. So in this case we need to find out the equivalent resistance, and then it is going to help us to find out the current in the circuit, and that is going to give us the required heat produced. And for the sake of convenience, let us assume we can put this value later on. Okay, let us assume this is a voltage source which is having a voltage of V, or otherwise let me do it different way. So let us assume that here between this point A and B we connect a voltage source of V. For the time being, we are just going to ignore this part. So if this is V, so our left side will be V and this will be equal to 0. And at P, let us suppose we have our Vp potential, and at Q, we are going to have our Vq potential. And then we can use our KCL at node P, then KCL at node Q. We get two equations and we sort it out. So you can say that our KCL at node P, and so first is from P to A, and that we can write as Vp minus V upon 1. And second is from P to B, and this we can write as our Vp minus 0 upon 2. And the third one is from P to Q, and this will be giving me Vp minus Vq upon 1. Okay, and we know KCL, the algebraic sum of the current is equal to 0. Therefore we can write that Vp minus V plus Vp by 2 plus Vp minus Vq is equal to 0. And the equation we are going to get this as 5 Vp minus twice Vq is equal to 2 times V. Let us call this equation number 1. And then we come to our KCL at node Q. KCL at Q. And we start with our from Q to A, and we can write this as Vq minus V upon 2. And then we can write this as from Q to B, and that will be our Vq minus 0 upon 4. And finally we are having Q to P, and this Q to P will be giving me Vq minus Vp upon 1. And once again the algebraic sum will be equal to 0. So we can write this as our Vq upon 2 minus plus Vq upon 4 plus Vq minus Vp upon 1 is equal to 0. And this is going to give us an equation that is our 7 Vq minus 4 Vp is equal to 2V. This is our equation number 2. And from these two equations we can easily find out, so you can see from equation 1 and 2, from equation 1 and 2 we get that our Vp is equal to 2 by 3 times V, and we get that our Vq is equal to 2V upon 3. Therefore now we can easily find out the value of the currents. Therefore we can say that our current from A to P, let us call this as our IAP, will be equal to V minus Vp upon 1, and this comes as our V minus 2 by 3 upon V, giving us V by 3. Then we can find out A to Q, and A to Q, let us call this as IAQ, will be equal to V minus Vq upon 2. So this comes as ever 1 upon 2 V minus 2 by 3 times V, which will be equal to V by 6. And then we can say total current from A that is our I will be equal to IAP plus IAQ, which gives us that our I will be equal to V by 3 plus V by 6, giving us V by 2. And from here we can say that equivalent resistance, that is our RAB, is equal to our Ohm's law V upon I. This is VI, we already found out. This cancel out, it comes as equal to 2. So please remember, in this circuit we have modified it slightly. We have connected a hypothetical voltage source V between A and B, and for the time being we have just ignored it, and based on this we were able to find out the equivalent resistance of this entire circuit, okay, which came as our 2 ohm. And now we are going to replace this entire circuit with the 2 ohm resistance. Now we can, so this will be our 2 ohm, that is our RAB, and it is now connected to a battery and its resistance. Okay, so this is our 20 volt and 2 ohm resistance, and therefore we can find out R equivalent of this circuit. R equivalent will be equal to over 4 ohm, that is our RAB, and let us call this as our RS. It comes as 2 plus 2, which gives us 4 ohm. And now let us assume that the current flowing in the circuit is of I. So we can say that of I will be equal to the voltage source. Let us call this as a V1. So this will be V1 upon our R equivalent. So V1 is our 20, R equivalent is our 4. This gives us 5 ampere. And now we can easily find out the heat dissipated. Heat dissipated that is equal to over I square R, because time is 1. So this comes as our 5 square multiplied by 2, and this comes as our 50 watts. And there was some doubt in this question that whether the bridge is balanced or unbalanced. Okay. But anyways, if the bridge is balanced, that is comparatively easy, and if it is not balanced, then we are going to use this node method to find out the current. Okay. And in this case, just remember that to find out the R equivalent, we have used a hypothetical voltage source V, and later on that V just cancels out. Next question. Okay, so it states that a current carrying solenoid is placed vertically and a particle of mass m with charge q is released from rest. The particle moves along the axis of a solenoid with the acceleration a that will satisfy. Okay, we have to find out basically what is the value of this acceleration. Okay. And we are given a solenoid that is placed vertically. So we have a vertical solenoid, something like this. And the charged particle is released from somewhere here, from rest, and it is going to travel through here. Okay, so this is the basic question, and obviously there will be two types of forces that will be acting on it. Okay. So we are interested in forces acting on the particle. acting on the particle. First one will be our gravitational force. Gravitational force, and that is our suppose Fg, which will be equal to our m times g, and it will be acting vertically downward. And second one will be our magnetic force. And magnetic force, and let us call this as our Fb, and that Fb is equal to our q times v cross b. Okay. And here b is the magnetic field, and in case of solenoid, this is directed along the axis of the solenoid. So we have to remember that our magnetic field B is directed along the axis of solenoid. So basically it will be vertical, and the direction of motion is also vertical, which is our velocity v. Okay. So we can say that our direction of motion, that is our v, is also vertical. And therefore we can write that our velocity is always parallel to our magnetic field. And if these two are parallel with each other, therefore we can say that their cross product will be equal to 0. And if their cross product is equal to 0, the magnetic force will be equal to 0. It means there will be no magnetic force on the particle at any given time. Okay. It means the only force that will be acting on the particle will be our mg. Okay. So we can say our net force, that is our F net, which will be resulting in acceleration, that is our ma. This will be equal to our Fg, which is nothing but our m times g. And here mass and mass cancels out, and this gives us that acceleration is equal to g, that is our acceleration due to gravity. Next question. It states that an air-filled capacitor of capacitance C filled with dielectric K is equal to 3 of width d by 3, where d is the separation between the plates. The new capacitance is. So we have to see how the capacitance is going to change when the dielectric is inserted in it. Okay. So we can divide this question into two parts: without dielectric and with dielectric. Okay. So we have first of all is our without a dielectric. And which means our original capacitance and let us call this as our C, and that C will be equal to standard formula epsilon naught A upon D, where A is the area and D is the separation between the plates. And now is our with dielectric. And with dielectric, let us try to understand that initially the entire space was uniform, having a thickness of d, but now dielectric is inserted. Okay. Therefore, the air gap thickness will be equal to, let us suppose it is inserted something like this, and its thickness is given as d by 3. It means the air gap, that will be our d minus d by 3. These are the connecting terminals. So we can say we are given that dielectric thickness is our d by 3. Therefore, you can say that remaining air gap thickness that is equal to d minus d by 3, which will be coming as 2d by 3. Okay. And area of the plates will be same, with and without dielectric it will be same. So it means now we have our two capacitors, one is having a dielectric and other one is having the air. So let's find out what will the capacitance of dielectric part. Capacitance of dielectric part, and let us call this a C dielectric, which will be equal to K epsilon A upon T, where here T is the thickness of the dielectric and K is a dielectric constant, so this comes as 3, and A area is the same, epsilon, and T is our d by 3. So this comes as 9A epsilon upon d, and we know that our C is equal to epsilon A upon d. So we can simply replace it here. It was C, let us call this as C1. Therefore, we can say that CD dielectric will be equal to 9 times C. And now we come to the air part. So capacitance of air part and let us call this as a C air, that will be equal to our epsilon A upon its thickness is our 2d by 3, and therefore we get capacitance because of the air will be equal to our 3 by 2, and this comes as epsilon A upon d, and this can be written as 3 by 2 times C. And now we find out the equivalent capacitance, and these both are in series combination, okay, one after the another. Therefore we can say that equivalent capacitance will be equal to 1 upon C is equal to 1 upon capacitance dielectric 1 upon air, and we simply substitute the value. 1 upon C will be equal to 1 upon, let us call this a C equivalent, 1 upon C plus 1 upon 3C by 2. Therefore we get that our C equivalent will be equal to 9 upon 7 times C. And in this case, if it is here, the filling was along around the thickness, okay? And if the dielectric is inserted along the area, then it will be a parallel combination, which means that if the dielectric inserted something like this, okay, then it will be a parallel combination. So if there is area division, it is a parallel combination, and if there is a thickness division, then it is a series combination. Next question. It states that 10 mole of oxygen is heated at constant volume from 30 degree to 40 degree centigrade. The change in internal energy of the gas is. And this we can solve using two methods. For the shortcut, it is, you can say, much more easier, and but we are going to get the same answer. Okay, that answer is not going to change, and we are given that it is a constant volume. So we are given this is our constant volume process. Therefore, we can say that our change in internal energy is for a constant volume is only dependent upon the temperature. Okay, so this will be N times C of V and change in the temperature. And we can easily find out our CV. Our CV will, one second, yeah, so CP will be equal to CV plus R. Therefore, we get that our CV is equal to CP minus R. And we are given that CP is 7 and R is 2. This is 7 minus 2, giving us 5. And change in temperature, that is our delta T, is about 40 minus 30, which gives us 10 degree centigrade. Okay, and there is no need to convert into Kelvin. Usually we do the Kelvin you can say calculation, but we need to find out the difference. So the difference will be always 10 degree, whether we solve it by centigrade or we solve it by the Kelvin. Therefore, we can say that our change in energy will be equal to 10 into 5 into 10, which gives us 500 calories. Okay. And yeah, so this is our change in internal energy. And in case the work done is being asked, it is a constant volume, so work done will be equal to 0. Okay, so the heat will be our, and you can say goes entirely into increasing the internal energy. And we are given this as oxygen. So oxygen is basically diatomic, ideal diatomic. And most of the time, in case of our internal energy calculation, we try to use our constant volume, C of V. Okay. Next question. And it states that in a double slit experiment, the distance between the slits is 0.1 centimeter and the screen is placed at 50 centimeter from the slit plane. When one slit is covered with a transparent sheet having thickness T and refractive index 1.5, the central fringe shifts by 0.2 centimeter. We have to find out the value of T. And this is basically a Young's double slit experiment. Okay. So the things that are given to us by standard notation, we are given the distance between the slits, which is a small d, is about 0.1 centimeter, and distance between the screen and the slit, that is our capital D, is our 50 centimeter. The refractive index of the transparent sheet, that is our mu, is 1.5, and the shift in the central fringe, that is our delta of y, is given as 0.2 centimeter. Okay. And it is given that we can just draw an approximate figure. So this is a screen, and there will be something like this, and suppose here we have placed a transparent whose thickness is given as T. So we can just convert all these into our SI units. So we are going to get distance will be equal to our 10 to the power minus 3 meters, and capital D will be equal to our 0.5 meters, and delta of U will be equal to our 2 into 10 to the power minus 3 meters. And in this case we have to remember that as we are going to add this thin transparent sheet of refractive index mu and thickness T, it is going to produce a additional optical path difference. So we have to remember that addition of our thin sheet introduces additional optical path difference, and this additional optical path difference, it is given as mu minus 1 times T. Okay. And this extra path difference causes results in you can say the shift in the entire fringe pattern, or you can say because of this we have a shift in entire fringe pattern on the screen. And the relationship between the shift, which is our delta of y, it is given as capital D small d and mu minus 1 times T. So this is the relationship between the fringe shift and the path difference. Now we simply substitute the values, and giving 2 into 10 to the power minus 3 is equal to 0.5, 1 into 10 to the power minus 3, 1.5 minus 1, and T we are supposed to find out. So we get our T will be close to equal to 8 micrometer. And okay, in this case we have to remember that the central fringe shift is independent of the wavelength. Okay, this is first point, and we can also say that the fringe pattern shifts towards the slit without the sheet. So these are the two important parts we have to remember here. First is that the central fringe shift is independent of wavelength, and second is that our fringe pattern shifts towards the slit without the sheet. Okay. So we have to remember these two things. Next question. It states that a wave propagates whose electric field is given by the equation. Find the direction of the magnetic field. Okay. And first of all, we are going to find out what will be the direction of the propagation. Okay. So you can say that direction of propagation and from the wave equation that is given, from here we can write the phase of the wave. The phase of the wave, and that will be equal to over omega t minus k times x. So it means from this particular equation we can say that the wave is propagating in plus x direction. So from here we can say that our wave propagates in plus x direction. So it means plus x direction. In terms of unit vector, we can write this as our I unit vector. Now let's identify what will be the direction of the electric field. Direction of the electric field, and we are given the equation that E is equal to 69 sine of omega t minus x. So obviously it will be perpendicular, therefore we can say that our field oscillates along plus y direction. Therefore from here we can write that the electric field will be parallel to our j unit vector, and we can use here basic properties of our EM wave. First of all, we know that the electric field is always perpendicular to our magnetic field. Secondly, we also know that electric field is perpendicular to the direction of propagation. Direction of propagation. And this is also true for our magnetic field. Is perpendicular to the direction of the propagation. And we can also write that both our electric field, magnetic field and propagation direction form a right-handed system. Okay, so this is important here. So we have to remember that our electric field, magnetic field and propagation direction form a right-handed system. And anyways, we can also find out their energy, that is equal to our, that is the cross product of our, I think, okay, let me write anyways, I'm not sure whether it is required or not. So you can say the direction of energy flow which is given with a pointing vector, and that is represented by S, which is equal to 1 upon mu naught, and this is our E cross B. Okay, so E cross B is nothing but our in terms of propagation direction. Now we can easily apply our right hand rule, and we can find out the direction. Okay. So we know that the propagation direction is our plus I, propagation direction is our plus I, and we have our electric field direction. Our plus J. It means that our cross product of electric field and magnetic field, we want it should be equal to our plus I. And as per our right hand rule, we know that our J cross K is giving us our I unit vector. Therefore, we can write that our magnetic field will be parallel to our plus K unit vector, or we can say in Z direction. That's why we call this as a right-handed system. Next question. And in this question, it is given that two mechanical waves of strings of equal length L, equal tension T, having linear mass density mu1 and mu2, ratio 1/2, find the ratio of the time taken for a wave pulse to travel from one end to the other in both the strings. Ignore the gravity. So this is directly based on the formula, that is wave speed in a stress spring, or we can say speed of a transfer wave on a spring. So we know that speed of a transverse wave on a string suppose that is our V, and that is equal to T upon mu, and they are having same tension, so wave speed is only dependent upon the, that is our mass, a linear mass density, that is our mu. So we can say that we are given that mu1 upon mu2 is equal to 1/2. Therefore, we can say that our mu2 is equal to twice of mu1, that is given to us. And we can divide this formula as our V1 is equal to tension is same upon mu1, and we can write this as V2 is equal to tension upon mu2. And so we can just solve for our V2. So we can say our V2 will be equal to, we substitute here mu2, this comes as T upon twice mu1 and its square root, and T upon mu1 is nothing but our V1. So this comes as our V1 upon square root of 2, and we are supposed to find out the time taken, okay, ratio of the time taken, okay, and the length is same. Therefore, we can say that time taken, suppose that is our T, will be equal to L upon V. Therefore, we can once again write for two strings, T1 is equal to L upon V1, and we can say that our T2 is equal to L upon V2. And so we can simply use our V2. So we get T2 is equal to L upon, and this is our V2 is V1 upon square root of 2, and this comes as square root of 2 L upon V1, and L upon V1 is nothing but our T1. So we get our T2 is equal to square root of T1, and ratio T1 is to T2 is equal to 1 is to square root of 2. Next question. It states that two rods of equal length 60 cm each are joined together end to end. The coefficient of linear expansion of the rods are 24 10 to the power minus 6 and 1.2 into 10 to the power minus 5. Their temperature are same and equal to 30 degree, which is increased to 100 degree centigrade. Find the final length of the combination in the centimeter. So in this case, we are going to use the basic formula, that is our, and we have to remember that although we have two rods which are connected end to end, okay, and their lengths are equal, but their coefficient of expansion is different. So we can say the change in length with the temperature of these two rods will be entirely different. Okay? So we can say that each rod expands independently. Okay? The expansion is not dependent upon each other. Therefore, we can write that our each rod expands independently. And that is given as expansion delta L is equal to L naught, initial our original length, coefficient, and change in temperature. So let's find out. We have two rods, so we can divide this at delta L1 will be equal to, for first rod it is our 60 multiplied by 24 into 10 to the power minus 6 multiplied by 70. Okay. So this comes as our 0.1008 centimeters. Therefore, we can write new length, which is our L1 is equal to our original length plus the increased length. So this comes as our 60.1008 centimeters. Similarly, we can find out for second rod. So you can see our delta L2 will be equal to our 60 times 12 into 10 to the power minus 6 times 70, and this will be coming as 0.04 centimeters. So its new length, let us suppose L2 will be equal to original length plus increase in the length, which comes as our 60.054. Therefore, our length of the combination, let us put this here, L final will be equal to L1 plus L2, and we simply L final will be equal to 60.1008 plus 60.0504, and we get this as our 120.1512 centimeters. Next question. It states that a curve is given between potential energy of the particle and its position on the x-axis. Theta 1 is given as 1, theta 2 3, and theta 3 minus 1 by 2. If these are the forces FAB from A to B, similarly FBC, FCD, FDE are the forces during B to C, C to D, and D to E respectively, arrange the magnitude of these forces in a decreasing order. So here let me draw the graph. So to paste it, 1 second. Yes. So the graph is something like this. And this is about A, B, C, D and E, and this is given as about theta 1, this is about theta 2, and this is about theta 3, and this is our energy U. This is our X. Okay, anything else? No, only this much is given. And so let's come back to the question. And one second. Okay, so we are given the angles and we are given the forces. We are given the tangent of the angle. So we are given the tangent of theta 1 is our 1, tangent of theta 2 is our 3, and tangent of theta 3 is our minus 1 by 2, and we are given the forces also. And we know that our force F is equal to our rate of change of our energy, and we are already only asked about the magnitude, so we can say this is equal to our du by dx magnitude. Okay. So basically, if we see from the graph, we can clearly see that our steeper is the slope, larger is the force, and the sign, that is our negative or positive, that affects only the direction part. There is no effect on the magnitude part. So this minus is not of that much of importance. We are only interested in the magnitude. Okay, so we have to remember that the sign of the slope, positive, negative, it only tells us that the direction. It gives nothing about affects the magnitude. So let us define the region. So we can say from A to B, we are given that our tangent of theta 1 is equal to 1. Therefore, we can say that our force FAB is equal to 1. Then we have our from B to C, we are given that our tangent of theta 2 is equal to 3, and therefore FBC, okay, we are interested in magnitude only, is equal to 3. And finally, we are having C to D, that is our graph is our horizontal. Okay. Therefore, we can say that our du by dx will be equal to 0. Therefore, we get FCD will be equal to 0. And finally, we are having from D to E, we are given that tangent of theta 3 is equal to minus 1 by 2. So we can say FDE, its magnitude is equal to 1 by 2. Therefore, FBC is our highest and FCD is our lowest. So you can say that our FBC is greater than our FAB, is greater than our FDE, and is greater than our FCD. Next question. It states that find the volume flow rate in the venturi meter given below, in which the water is flowing. The cross section area A and B is ratio is given as 2 and A is given as square root of 3. Density is also given to us. So let me draw the figure, then we come back to the question. Okay, so we were given that we have something like this. And the points are also given to us. We are given that this is our capital A and this is given to us as our small a, and this is point A and this is point B, and the level of the water, there is a liquid inside it, and so here it is like this, and here it is also like this, and the level of the water is, this is given to us as a 5 centimeter. That is, yeah, I think that's a given thing. Okay, so one second. In this case, we can use our, you can say, both the theorems, and so we are given that this is point A and this is point B. So we are given that at A the area of cross section is our capital A, and at B the area of cross section is our small a, and the ratio is given to us, and the height difference, this is our important, so you can say the height difference let us suppose that is H. Sometimes it is also called as a manometer height difference, and that is our 5 centimeter, which will equal to 0.05 meters. So first of all, let's find out what will be the area at B, that is small a. So you can say that area at the throat, area at B, which is a small a, and it is capital A divided by 2, which comes as 3 by 2. And then we can use the pressure difference from the manometer. Pressure difference from manometer, and we can write this as our pressure at A minus pressure at B will be giving us rho G H. and these are given to us. So we can say this is about 1000 times 10 times h 0.05. G we have taken as h, so this comes as about 500 pascals. Now we can apply the Bernoulli's theorem. Sometimes if you know the formula directly, you can use it, but if you do not use it, know, we can just solve it like this. Then we can say that our Bernoulli's theorem and our pressure at A divided by rho plus VA square upon 2 is equal to pressure at A divided by rho plus velocity at B square divided by 2. Okay. The rest of the things we can just cancel it out. So we get from here that PA minus PB will be equal to rho by 2, and this is our VB square minus VA square, and PA minus PB is, we just found out, that is our 500. So this comes as our 500 is equal to 1000 upon 2 and VB square minus VA square. So these cancel out, so we get VB square minus VA square is equal to 1. Now we can use the equation of continuity. Equation of continuity, which gives us that area VA and small a times VB, and we already know their respective values. So this gives us root 3 VA is equal to root 3 by 2 times VB. Therefore we get that our VB is equal to, this cancel out, is equal to 2 times VA, and we will let us call this as equation number 1. So from equation 1 we get this as our 2VA whole square minus VA square is equal to 1. So we get that our VA is equal to 1 upon square root of 3, and VB will be giving us 2 square root of 3. Now we can find out the volume flow rate. Volume flow rate, which is our Q is equal to A times VA. So we get our Q is equal to root 3 times 1 by root 3. It cancels out, so we get this as 1 meter cube per second. Next question. It states that a planet revolving around Earth in a circular orbit of radius 1.5 r is transferred to a circular orbit of radius 3 r. The net energy needed in doing so is x times 10⁷ joules. Mark the nearest integer to x, where r is the radius of the Earth and planet is, we can say, is our satellite. So we are going to start with the energy associated with the satellite in the circular orbit. We can say that energy of a satellite in circular orbit, and let us put that energy is our E. E will be equal to minus G capital M small m and 2 times R. And now let's find out, because we are moving it from a lower orbit to the higher orbit, 1.3 r to 3 r. So we can divide this formula into two parts, E1 as well as E2. Okay. So we can say the initial orbit for that, let us call this E1, and E1 will be equal to our minus GMM, and this is 2 times 1.5 times R, which gives us minus GNM, and this is about 3 times R. And then we come to a final orbit, which is our E2. This will be minus GMM, and twice this is our 3R, giving us minus GMM times 6R. Simply they are difference in energy. You can say energy required that is delta E will be equal to E2 minus E1, and we substitute the values. Okay, so we have our this GMM M upon R, we can take as common, so this will be coming as our minus 1 upon 6, and minus 1 upon 3, and minus 1 upon 6. Therefore we get this energy is equal to our delta E will be coming as our GMM upon 6 times R. So this energy is positive, so we can say that a sign is positive rather, so energy has to be supplied, obviously, if you are going to move from this. And what, okay, then we substitute the values now, and so I think something is missing here. Mass of the satellite is missing. Okay, anyways, it's not a big issue. Okay, if we substitute the values, we are going to get the answer. And next question. So we are given that in a microscopic objective is having a focal length of 2 cm and eyepiece is having a focal length of 4. The tube length is 32. The magnification produced by the microscope for the normal adjustment is. Okay. So normal adjustment means the final image is at infinity, or we can say our eye is relaxed. So you can see our normal adjustment means that our final image it is formed at infinity, and this we can use the direct formula in order to find out the magnification. We are supposed to magnification, so we can say that M is equal to L upon F naught multiplied by D upon Fe. We can use different one also. For eyepiece we found out M1, for objective we found out M2, then we multiply them. Okay, but we can just simply substitute the value. The length is given to us as 32 and focal length is given as 2, and something missing. And D is our distinction vigilance, that is 25, and we have eyepiece is given to us as a 4. Therefore we can just cancel out this, goes by 8, this goes by 4. The magnification will be coming as our 100. We can individually also find out M1 and M2, then solve it out. So this was up till here was our session 1, and then we come to our session 2 now. And in this case it states that in the circuit the battery has a EMF E, internal resistance R. It is connected to external load resistance R as shown in simple series circuit, battery with R and EMF E in series with R. Find the value of R in terms of small r such that maximum power is dissipated across the external resistance. So we can just draw the figure. Internal resistance small r, and battery is given to us as, let us suppose, E, EMF E, and this is capital R. So we have to find out this value of R in terms of this small r for maximum power transfer. For that we are going to find out our current I. So you can see that current I in the circuit will be equal to our EMF and divided by the total resistance. And power dissipated in the resistance R you can see power dissipated in R, this will equal to P is equal to I square R. So we get this as E square R upon R plus whole square. And for maximum power we can use our derivative method, differentiation, and derivative and substitute equal to 0. So we can say for maximum power our dP upon dR should be equal to 0. Okay. And this differentiation gives us that our R is equal to small r. Next question. It is asked that a prism has a refractive index mu square root of 2, prism angle A 90. It is a right angle isosceles prism with the refractive index angles are 45, 45, 90. A light ray is incident of one of the faces containing the angle 90 degree. Find the angle of incident I on this face such that the refractive index of prism grazes along the second refractive surface. Okay. Therefore, we can just draw the figure, and suppose this is our incident ray of light, and here it is just going to graze our this is an E, and this is our angle of the prism, and therefore we are going to find out the grazing means that angle of emergence, or we can say that emergence at the second phase, the internal angle of incident must be the critical angle. Okay, that we have to remember. Otherwise, even if you solve it, you can solve it otherwise also, but this is a little bit shorter. So we can say for grazing emergence at the second phase, the internal angle of incidence internal angle of incidence must be critical angle. Must be critical angle. Therefore, we can write that sine of IC will be equal to 1 upon mu, which gives us 1 upon square root of 2, which gives us that our critical angle will be equal to 45. That means the ray inside the prism strikes the second face at an angle of 45 degree. 45. Now, from the geometry of the prism, if I join them, and our internal angle is, let us suppose this is our R1 and this is our R2, then the summation will be equal to the angle of the prism. So you can say from prism R1 plus R2 will be equal to angle A, and angle A is our 90. Therefore, we can find out that our R1 will be equal to 45 degree. And now we use the Snell's law at the first face. Okay. So let us call this as point A, this is point B. So this calculation is at point B, Snell's law at point B, and now we are going to use Snell's law at point A. Snell's law at A, and if the angle of incidence is suppose I, therefore Snell's law gives us sine of I is equal to mu times sine of R1. Now it is easy to solve. So we have a sine of I is equal to mu is square root of 2, R1 is 45, so sine of 45 is 1 by square root of 2. These two terms cancels out, this comes as 1. Therefore, we can say that the angle of incidence is about 90 degree. Next question. It states that a block of mass m is at rest with respect to hollow cylinder which is rotating with the angular speed omega. The radius of a cylinder is r. Find the minimum coefficient of friction between the block and the cylinder. Okay. So we are given that we have a cylinder and suppose this is the axis of the cylinder and it is rotating angular speed omega, and there is a block M, suppose somewhere here, and it is at rest. Okay. So if it is at rest, it means all the forces, it will try to move in a downward direction, so friction will be acting upward. Downward we are going to have this mg. Okay. Otherwise there will be also a rotational part also. Okay. So let us try to understand the motion, and we are given that block is at rest with respect to the cylinder, and let us assume that radius of the cylinder is our r. So we are given that block is at rest with respect to cylinder. Okay. So it means that block moves in a horizontal circular path horizontal circular path of radius capital R, and angular speed will be equal to omega. Therefore, you can write that its linear speed V will be equal to omega times R. Okay. And we know that the block needs a centripetal force towards the axis of the rotation. Okay. So let's define the forces acting on the block. Forces acting on the block. So we are going to have our weight, whichever mg, and in the downward direction, and we are also going to have a normal reaction, and that will be radially inward. So we are going to have a normal in this direction, radially inward. Radially inward. And finally, we are going to have a friction which is F, and that will be acting vertically upward. And let us write for our radial centripetal force. And that is our Fc will be equal to over m omega square times R, and this will be nothing but our normal force is going to provide it. And then we have our vertical, and you can say for vertical, because it is in equilibrium, so the friction is going to balance our mg. And we know that our maximum value of friction will be equal to coefficient of friction times normal, and that will be equal to our mg. And n we already know, so we can add this as mu, and this comes m omega square R is equal to our mg, and we can find out from here our coefficient of friction, that our mu minimum will be equal to g upon omega square R. Next question. Okay, this is the same question. So in this question it states that, keeping the significant figures in view, find the sum of physical quantities 50.01, 0.2 and 0.013. Okay. So in this case we have to remember that we are going to use the rule of addition or subtraction in case of significant figures, and in that case the number of decimal places will be equal to the least number of decimal places. Okay. You can say that for our sum or subtraction of our significant figures, we should remember that the final answer they should be having same number of decimal places, same number of decimal places as the least number of decimal places. So it means the least number of decimal places is nothing but our this part 1.53.2. Okay. So if we add them, this is 50.01 plus 153.2 plus 0.123, this will be giving us 203.33 meters. But like I said, it will be the least number of decimal places, and that is our 1. So we get this as our 203.3. This is our final answer. And in case of multiplication, okay, we can say that only the significant figures matter in case of multiplication and division. In case of addition and subtraction, decimal place matters. So you can just remember it like that. Next question. It states that a diametric gas does 100 joule of work in isobaric expansion. The heat given to the gas is. So we have isobaric process. So we are given that we are having isobaric process, and for isobaric process we know that our work done W is equal to nR times delta T, and our heat, that is Q, is equal to N times Cp times delta T, and our ratio, adiabatic ratio, that is our gamma, is equal to Cp upon Cv, and our Cv is equal to our R upon gamma minus 1. So let's find out the specific heats. So we get that our C of V will be equal to R upon 1.4 minus 1. This gives us 2.5 times R, and C of P is equal to C of V plus R. So this comes as 2.5 R plus R, giving us C of P is equal to 3.5 times R, and work done is given to us as 100 joule. Okay, so we can just look at here. Therefore we get that W is equal to nR delta T is equal to over 100. Therefore the heat supplied which is our Q is equal to over N C of P multiplied by delta T, and we can say is equal to over 3.5 times N R delta T, and giving us 3.5 times 100, and which gives us that the heat supplied is equal to our 350 joules. Or in case of shortcut, we can also use that Q is equal to gamma minus 1 times W. We can also use this shortcut in order to find out our this heat given. Gamma is 1.4 So that will be also giving us the same answer. Next question. The magnetic field due to current I flowing in the following circuit at the center C. Okay, the circuit is given something like this, and it is connected with wire like this. Okay, suppose the current flows in this direction, and this is center C. So we have a circular loop. Let us suppose the radius is our R, and so this our net field at A will be equal to field due to the loop as well as the field due to the wire. Therefore, we can say that our magnetic field due to the loop at the center is our mu naught I upon 2R, and its direction will be out of the paper. And then we are having magnetic field due to wire, and that will be equal to our mu naught I upon 2 pi R, and its direction will be into the paper. You can simply use the cross rule into paper. So both the directions are opposite. Therefore, we can say our net magnetic field that is supposable B is equal to magnetic field due to the loop minus magnetic field due to the wire, and we substitute it, we get B is equal to, this will be a mu naught I upon 2R 1 minus 1 upon pi. So this will be our net magnetic field due to the in the given circuit. Next question. It states that the terminal velocity of a spherical ball of radius 6 millimeter in a liquid is given as 20 centimeter per second. Find the terminal velocity of the ball of 3 millimeter of radius in the same liquid. Okay, this is quite easy. It is based on the Stokes law. So you can say that our Stokes law and that gives us that our terminal velocity Vt is equal to 2R square, the difference in their density multiplied by G and 9 times our mu, and rest of the things are constant here. We only can say that our terminal velocity is proportional to radius square. So we can divide this into two parts. Vt1 is proportional to our R1 square, and terminal velocity for second is proportional to our R2 square. So we can simply take the ratio. Vt1 upon Vt2 is equal to R1 upon R2 whole square, which comes as 6 upon 3 whole square, giving us 4. And therefore we can say that our Vt1 is our 20, so we can our Vt2 is equal to 20 upon 4, giving us 5 centimeter per second. And in case of terminal velocity, we have to remember that total drag is basically a balanced condition. Okay. The viscous drag, it is one direction, upward there will be forces, and this will be entirely balanced. That is the basic of our terminal velocity. Next question. It states that a particle executing SHM has a kinetic energy 203, angular frequency 176, the frequency of SHM, simple harmonic oscillator is. And we know that our omega is nothing but our 2 pi f. Now we can say that our f is equal to omega upon 2 pi. So we get this as 176 upon 2 into 22 upon 7, and this gives us 28. So this was quite easy, straightforward, nothing much is, it is, 1 second. Okay, next it states that the width of the river is 200 meters. It is flowing with a velocity 10 meter per second. A boat can move with a speed of 20 meter per second with respect to the river, wants to cross the river in a minimum time. The displacement along the river bank is. In this case, we have to find out the minimum time, and minimum time means that boat must be using the entire speed traveling perpendicular to the river flow. So it means if this is our river bed, and let us suppose this is given to us as this is D, and river is flowing in this direction. Therefore, the boat should be trying to always travel in this direction. Okay, that is the perpendicular to the river flow for the minimum time. You can say for minimum time, boat must always travel perpendicular to river flow. So which is nothing but a straight path between the two banks. Therefore, we can write that our T minimum will be equal to the distance and the velocity of the boat, that is about 200 divided by 20, which is about 10 seconds. Now we can find out the displacement. So you can say the displacement that is our capital D will be equal to velocity of the river multiplied by the minimum time, and the velocity of the river is about 10, this is about 10, which gives us 100 meters. So it means it, because of the river, it will be displaced by this much amount. Okay. So because of the river, the actual direction in which the boat will be able to travel will be something like this. It will try to travel always in the perpendicular direction, but because of the river traveling, it is going to force the boat to have a displacement of D, that is our velocity of the river multiplied with the minimum time. Okay. And so for minimum time, the boat should be traveling perpendicular, and for minimum displacement, the boat should be traveling up the stream. Okay. So that is for minimum displacement. So these were the few questions, memory based questions rather. Okay. There might be some problem in the data also, it might be possible. Okay. But the basic concept or the basic idea of the question, you get the feel. So we try to we try to solve session 1 and session 2 for the exam which was held on 21st. That's the first day of the JEE Main. And so approximately I think we try to solve something around 26 approximately, I don't remember, of both the sessions. The first session we were having more questions. In the session 2, in the evening session, the question were a little bit less, but we get the basic idea of the questions. So this completes all the questions, not all the questions, but some of the questions which were memory based for the JEE Main that were held on first day, that is 21st of the January 2026. So please remember once again, these are the memory based questions. Okay? These are not the actual questions. So data might be somewhere here and there. Okay? Sometimes the framing of the question is also a little bit different. So this completes the questions. Thank you.